Now first we will derive a differential equation for our simple harmonic motion. So suppose let a particle of mass m, let a particle of mass m oscillated in simple harmonic motion. So it is oscillated at simple harmonic motion. So now simple harmonic motion. So now at time t, if its displacement is x and its displacement is x, then we can say the velocity of this particle is, we know, which is actually equals to dx by dt. It's a differentiation of displacement with respect to time, and the acceleration will be equals to d square x by dt square. Why this d square x by dt square? Because we will differentiate the value of velocity. So acceleration is equals to differentiate with respect to time the velocity term, and we know the term of this velocity is actually equals to dx by dt. So we can write this thing as a is actually equals to d square x by dt square. So I hope you understand how this term come. So now we know force F equals to m. This is the we find out this equation from Newton's second law. Instead of a, we can write this equation, which is actually equals to d square x by dt square. Okay. Now, since force or acceleration is proportional to displacement and is in opposite direction, as simple harmonic motion says, so we can say that force is proportional to the displacement with opposite direction. So we can say this thing. We find out the equation of force is m is actually d square x by dt square proportional to minus of x. To eliminate this proportional sign, we use a constant k, which is called force constant. Then I can write this equation is m of d square x by dt square is actually equals to the minus of k of x. So suppose this is our equation 1. Now as we know from our previous equation, we know our acceleration a, for a simple harmonic, our acceleration a is actually equals to the minus of omega square x. Our acceleration a is actually equals to the minus of omega square x. So this term is representing our acceleration term, and we can write this thing as d square x by dt square is actually equals to minus of k by m into x. So this terms is actually representing our acceleration term, we know from that part. So instead of a or this d square x by dt square, I can write this term minus of km by x. So I can write this term minus of km by x, which is actually equals to minus of omega square x. Okay. So if I cancel out this x and minus, then I find out that our omega square is actually equals to the k by m. So instead of k by m, I can write this omega square. So instead of k by m, so from this equation 1, instead of this k by m, I can write omega square. Okay. Then if I take this term in the left hand side, then I will get d square x by dt square plus omega square x equals to 0. And this is known as differential equation of a particle executing simple harmonic oscillation or simple harmonic motion. So I hope you understand this term, this differentiation term. This equation sometimes is very important for our some small question of like MCQ question. Let us take an example of this MCQ question. Suppose in our question given that a differential equation for a particle of a particle, the differential of equation of a particle is d square x by dt square plus 9x equals to 0. Now I have to find out what is the angular velocity of this, or angular frequency of this. What is the angular frequency of this? Is the angular velocity of this term omega, or what is the angular velocity of this particle? Okay, and here our choice is 2, 3, 9, 5. So how can you find this thing? We know this differential equation. Here I find out this omega square term, and this term and this term are matching. So is 9 will be equals to our omega square. So our omega square equals to 9. So what will the omega? Omega equals to 3. So what is the angular velocity or angular frequency of this term? Which is 3. So in that manner we can solve some MCQ questions of this differential equation. Now I will derive some terms, some related terms of simple harmonic motion. First term we'll just derive is time period. In our previous video, we know the equation for our displacement x is actually equals to a sine omega t plus del. Here x represent displacement, a represent amplitude, omega represents angular frequency or angular velocity, t represent time, and this del represent our phase difference. Okay, now when our time is increasing by 2 pi by omega, so when our term when our time is actually increasing by t plus 2 pi by omega, we increase our time with 2 pi by omega, then our this equation will be looks like this: x equals to a sine omega t plus 2 pi by omega plus del. Okay, plus del. So what will be this? Will be actually equals to a sine omega t plus 2 pi plus del. Okay, or I can write this thing as a sine 2 pi omega plus del. Not omega, it will be actually omega t plus del. 2 pi plus omega t plus del. So we know for this side, when we add we add something to the 2 pi, then it will actually equals to comes to the first position. Then I will get a sine omega t plus del. So from this thing we find out that after time 2 pi by omega, the displacement of the particle becomes the same, or the equation is same to the equation of 1. So from that we can say that our time period t is actually equals to 2 pi by omega. So this is one term we will use for simple harmonic motion. For simple harmonic motion we will use this equation where time period t is actually equals to 2 pi by omega. I hope you understand this equation. Now another point. So how to be the frequency. Now we know as t equals to 2 pi by omega, then we can write this thing as t equals to 2 pi by omega, and we know the value of omega square equals to k by m. We just proved this in our previous slide. So instead of omega, I can write the omega equals to actually root over k by m. So instead of omega, I can write 2 pi root over k by m, or I can write 2 pi root over m by k. So this is another term we derived from this equation. So this is the equation for our time period. So what will be the equation for our frequency? So we know our frequency f, or sometimes we represent this thing as eta, is actually equals to 1 by t. Okay, so I can write this thing as omega by 2 pi, or I can write this thing as 1 by 2 pi root over k by m. So this is the equation for our frequency, and the last equation is our angular frequency. And we represent this thing, our angular frequency, as omega, and we know omega equals to root over k by m, or I can read this thing as omega equals to 2 pi by t from this formula. So this is the some term related to simple harmonic motion. We use this term to solve mathematical problems. I hope you understand this term and the differential equation. That's all for today's video. Please like this video and do subscribe to our channel. Thank you.